Great. Let's get started. Today I'm presenting. Thank you for the invitation, Jimmy. So today I'm going to present my paper, our paper in Europe's 2024, which is called Multiview Scene Graph. So first of all, a bit of introduction or background of myself. So I'm currently a second-year PhD student in computer science at New York University Courant Institute. Previously, I also did my master's in New York University, and I did my bachelor's back in China in Tsinghua University in electrical engineering. And my current research interest includes spatial intelligence and building scene representations that are useful for robotics to do task planning. And this is the outline of today's presentation. And let's get started. So we know that robots need spatial understanding of the environment that they are operating in to plan their tasks and motions. No matter it's autonomous vehicles, household robots, or delivery robots, understanding and representing the scene is very important aspect of their spatial intelligence. And let's get okay. And the carrier of their spatial understanding ability is often an appropriate spatial scene representation. And this scene representation usually emerge from visual inputs and can take different kinds of formats. For example, it can be implicit, where it's just like neural rendering or just hidden in the model's parameters, or it can be explicit. And when it's explicit, sometimes it's metric. For example, point cloud, mesh, occupancy maps, 3D scene graphs, and perhaps 3D bounding boxes, and even 3D Gaussian splatting. And sometimes it can be explicit and topological, such as the post graphs with loop closure in simultaneous localization and mapping SLAM, or the co-visibility graph in structure and in structure from motion (SFM). And note that I would like to note that this is not another rigorous taxonomy. I'm just trying to roughly divide them for clear concept. Sometimes they are intertwined and interdependent. They could be, for example, topometric, such as, for example, 3D scene graphs are usually built from metric information like 3D information, but the format, the eventual format is a topological graph. And for example, in a structure from motion, where you start with a co-visibility graph, but eventually you get a metric reconstruction. And so you've seen all these kind of scene representations that are super useful, have a lot of great literature. The question I am trying to explore in this work is, how do our humans and animals build scene representations in our mind? We in the work we break down this question step by step. So first of all, what is the input? I believe the input is largely also from visual signals, from what you see and we memorize. And what is the format? Of course, it's a bunch of neurons because it's a brain. But what do these neurons care about is the key question here. So I would like to invite you to imagine if you are in NYU in Manhattan, and at some point you're sitting at my office in 65th Avenue, and you just want to grab a coffee at a nearby roaster called Stompton Roasters, and you want to take the coffee to the Washington Square Park, where we're just near NYU to enjoy your coffee. So if you're familiar with this neighborhood, what you instantly imagine is that, okay, this is where you're gonna start off. This is the building of the office, and then you're gonna walk on the street, and then until you saw this nicely decorated green gate and door, and you know that, okay, here I'm at the McDougal Street, right? And this is the entrance of the coffee roaster, and then you can execute your operations of getting a coffee, order your coffee, grab the coffee. And then you will take the coffee and continue walking until you reach this fountain, this park, which is the famous Washington Square Park in downtown Manhattan. So in this whole process, you imagine you're walking in the city and doing all these actions. You would realize that in our mind, we don't perceive and memorize the scene metrically. By the exact meters and degrees, you wouldn't think in mind that, okay, I'm gonna go straight for like 100 meters exactly, and then I'm gonna turn right for 90 degrees, and I'm gonna continue going straight for 50 meters until I reach some certain location. But you will remember all these landmarks, these locations. So that means we build a cognitive map that is topological based on these landmarks, visual appearances, and their correspondence. So that's the inspiration here, which leads to this question: can we equip our machines with similar spatial intelligence or a similar format of scene representation? So the research question is how to be in this paper is how to build a human-like scene representation. And based on the thought experiment, I would say that we just covered, we can break down this research question by asking what are the fundamental elements in this human-like scene representation. So first of all, we've seen that it's topological. We have all these landmarks, these locations that are just in our memory or just what we can see. And metric information such as meters and degrees are great, of course, but not always required to have this kind of navigation map or cognitive maps in our brain. And secondly, we realize that correspondence or visual correspondence between that can associate locations and entities from multiple views, between multiple views, and your memories is the key relation in this kind when you construct this representation in your mind, right? So that gives that can help us refine the research question into how to build a topological scene representation from visual input, which is the essential question that I'm trying to answer or trying to explore in this work. So that's the refined research question. And with that, we propose in this paper, we propose multiview scene graph as such kind of scene representation. And first of all, so it comprises exactly the two elements that we just discussed. So first of all, the relationship in this graph is multiview correspondence, which arguably I would argue that it is the most natural spatial relationship that that you can get from just multiview RGB observations, imagery observations. And secondly, it's a topological representation. So it's a scene graph, so it's a topological representation. And we've seen all these different kinds of scene representations. So we want to know, so what's so good about it versus the metric-based representation? So first of all, like we said, it resembles human perception, human spatial intelligence. And secondly, it's almost always available because multi-view correspondence is so natural and so easy to get. As long as you have multiple observations, you can sort of try to build a multi-view correspondence. And because there's no localization or depth information that is involved in this process, so it's robust to metric error. If you're relying on metric measurement to localize yourself and build the map, if the metric information has an error, then your map could be distorted. You ended up thinking that you are at a different location where you just continue on to map to build the map, and then the map is completely messed up. And like I said, it's not a rival to the metric-based representation. Instead, it's like a complement. If you have a topological representation, you can always add the metrics later as an add-on. And having a good topological representation can almost always benefit a metric reconstruction or metric representation later on. For example, in structure from motion, you have a very good co-visibility graph. You can build a better structure from motion. And you can sometimes maybe iteratively optimize these to the metric side and the topological side by estimate the poses and give that to the topological side and refine the topological representation and then build a better metric representation. So we would argue that it's a complement to the metric-based representations that are abundant nowadays. And then let's quickly cover some related works. So there are two lines of literature that I believe are conceptually related. One is scene graph, another is scene mapping. So scene graphs were proposed in image originally and describing the object relationships, and then it was extended to 3D as a format of scene representation. So basically, it represents a scene as a topological graph with objects and sometimes with also rooms and camera positions as their nodes, and they are built on usually given or estimated 3D metric information beforehand. And they focus on object relationships. And another line of work that are conceptually related is mapping. For example, simultaneous localization mapping. It's a fantastic line of literature. There are some of those works rely on metric information such as poses and build metric maps. And some of those works build topological maps that are particularly optimized for the purpose of navigation or some other downstream tasks. Here, in this work, we propose Multiview Scene Graph, MSG, that we position as exploring a different dimension by just building purely topological scene representation and just evaluate the quality of building of the graph you can build as the means to evaluate the spatial understanding you can get from purely visual inputs. And another aspect of related works are the functionally related. When we talk about how to build MSG, we mentioned about multiview correspondence, and this leads to the literature in place correspondence and object correspondence. For the place correspondence, there's a line of work called in robotics perception called visual place recognition, where where you localize a robot based on its current observation, an image, and a database of the images of the previously visited locations that it stores. And the approach is usually taking, the approach that you usually take is an image retrieval approach, where you extract features from the current image and extract features from a database. And then you use these features to build descriptors, and then you retrieve the most similar images based on these features or descriptors. And another correspondence is object correspondence, which are corresponding objects, bounding boxes, or segment masks between different views and different temporal time step. And these line of works include multiview object tracking and associating object across views and video segmentation. For MSG, for multiview scene graph, the scene graph, the MSG bridges these two fields for a general topological scene representation that combines both place correspondence and object correspondence. So without further ado, this is the overview of the task multiview scene graph of like what we're building. So basically, it takes unposed RGB images as input and outputs a place plus object graph. In this graph, we basically answer two questions. One is whether two images are same place. And if they are same place, meaning that they are taken at the close by camera positions, then they should be connected on the graph. And the second is whether two objects you see from different views are actually the same object instance. And if they are the same object instances, they should be always merged as just one single node and connected to the places where they are detected. So in that there's a object association process that is going on, where you see the same object from different views and you know that it's the same object. So it's the same node rather than two different nodes on the graph. And to give a formal definition, checking the time, to give the formal definition of the multiview scene graph, we can write it as this following. So the input is a set of unposed images, like the set X, and then the graph is represented as the place object graph, where you have two kinds of nodes: place nodes and object nodes, and place edge EPP and place object edge EPO. For the place part, as you can see painted in red on the right, the place nodes are equal, essentially the image nodes, where each image just corresponds to a node for potentially a place. We're just following the conventional definition in visual place recognition literature, and the place edge is between the place edges are between these images that are from the same place. By same place, we mean that there is a small translation and rotation differences between the two images. And then, as painted in cyan on the right, for the object part, the object set O captures all the objects in the scene, where the same object is detected from different images across views, and they should always be one object node in the set. And the place object edge are those edges that connect the place and the objects that appears in those places, like you see painted in cyan on the right. And then now we have proposed this format, this task, multiview scene graph. Then the next question that follows is, how do we evaluate the quality of the graph that you can build? So a graph is the graph can always be associated with a binary adjacency matrix, where the ones in the matrix correspond to an edge between the corresponding node of the rows and the columns, right? So here for MSG, for multiview scene graph, the adjacency matrix A can be decomposed into these 4 different parts. APP meaning the place part, APO and AOP meaning the place object part, and AO is of course the object part, which is not covered in this framework, but can be an add-on later. So the task of MSG is to predict a graph G hat compared to G, and that also comes with a predicted matrix, the adjacency matrix A hat. So the evaluation is happening between A and A hat by trying to find how much they can align by calculating the intersection over union or IOU between this A and A hat. And because we see that the adjacency matrix is symmetric, and the object part is not included, so it eventually boils down to comparing the APP with A hat PP and APO with A hat PO. And for the place part, for the APP part, it's relatively straightforward because you can always mark the images with timestamp, or if it's not a temporal, if there's no temporal audio, if it's not a video, if it's just an image set, you can always mark them with IDs. And so it's relatively easy to align the APP with APP hat and just calculate the intersection over union because the two matrices are binary. But for the place object part, it's not that trivial because you can't always predict the exact same number of object as you see in the ground truth. And also the orders of the objects or the IDs you assign to these objects that you detected cannot always be guaranteed to be the same as you get from the ground truth from the annotation, which is there is a what we say a truth to result matching issue in the process of evaluating a place object IOU, which is similar to what you usually get in multi-object tracking literature. So to still calculate the PIOU, we calculate the truth to result matching, and this matching will give you sort of like a permutation matrix that can reorder the objects that you see from that you predict from your predicted graph like this. And with that, you have a alignment between the predicted graph and the ground truth graph, and so that you have an aligned predicted matrix, adjacent matrix, and the ground truth adjacent matrix. And finally, that makes it possible to calculate the place object IOU. And then comes our method. How do we tackle the problem of building a multiview scene graph from purely unposed imagery inputs? Then let's introduce it step by step. So first of all, as I just said, the input are unposed RGB images, and then we send these images into a frozen image encoder to get the image tokens, or if you use convolution networks, it's image features. And we can use an off-the-shelf object detector, which is also frozen, to get the detection results, which are represented as bounding boxes of objects. And then you can reshape the image tokens into an image feature, or you can just directly take an image feature from convolution networks. And then you can apply the object bounding boxes on the image feature to crop the object features with the bounding box to crop the object features from that. And because we are trying to incorporate the place association part with the object association part, so we want to build it in a unified framework. And how do we do that? We just simply treat the place as if it's a big object that covers the entire image. So we just use a whole image bounding box that can just attend to every feature on the feature map, and then extract the place information as the place queries. And with the place queries and the with the place features and object features subtracted from the feature maps, from the pre-detected results, we can further use a transformer decoder that takes the bounding box embedding and the place and object features that you just get as the queries to the transformer decoder, and then use the image tokens that you get from the image encoder as the keys and the values for the transformer decoder. The intuition behind this design is that we believe context provides the important clue for place and object association. If you see an object from across views, but the background, the context are kind of similar, then you would probably think that it's the same object, but just viewed from different views. And if you always see a few very similar objects from two different images, then you will probably guess that these two images are taken at very close by locations. So we want to incorporate the idea of concept into this kind of modeling. And with that, the transformer decoder will output the context-aware image features or place features or an object features, and we further send it through the place hat and object hat to get. We simply supervise contrastive learning to get the place representation and the object representation. And here is an overview or the illustration of what you finally get from the method. You take the image input, you have the environment, and you take the image and where you get the RGB observation, and then you detect the object, associate the object in the place, and you can build a graph like that. Okay. Yeah. And then comes the experiment results. So we use a publicly available 3D indoor dataset, ARKit scene, made by Apple to build the 2D datasets that we can use in this task. And there are many scenes in the dataset. Not a single object is repeated across the scenes. And for the implementation details, for the detection part, we train on ground truth detections that you get from the dataset by converting the 3D object annotation to 2D bounding boxes, and we tested on the ground truth, and we also tested it with an off-the-shelf open vocabulary object detector called Grounding Dino. And for the backbones, after a few empirical testing, we find that Dino version 2 gives the best result. So we stick to Dino version 2 as our image encoder. And for the baselines, as we just discussed, there are two lines of works that are functionally related. One is the place recognition, another is the object association, object tracking. So for the place part, we compare to these three place recognition literatures, and we also compare to a post estimation paper because if you can estimate post between the images, you would know whether these two images are taken at the close by locations, right? And for the object part, we evaluate two object tracking papers. One is tracking object bounding boxes, and another is associating object segmentations across the video. And so besides those baselines, we would also want to know whether our designed unified framework, AOMSG, attention associated MSG, is better than just simply using the same backbone and just build on top of it a few layers of probing heads. So we also compared with baselines called SEP MSG, which stands for separate MSG, and there are three of those. The separate MSG direct, meaning that you just extract the features from the image feature map, from the image encoder, and then just directly compare the similarities between the image features and object features to determine whether it's the same place or same object. And similarly, SEP MSG linear and SEP MSG MLP stands for the model that append a linear head or MLP head as a probing head on the frozen encoders. Yes, and for the results for the place part, besides the PPLU that we designed, we also evaluated the recall at one, which means that you retrieve the most similar image from all the previous observations, and you check whether this image is exactly from the same location, from the same place. And we see that for the post estimation baseline Mickey, which takes video as input. Our model takes unordered image set as input. It takes video as input, so it can almost always get the required one right, because most likely it's just an adjacent frame in the video stream. But it suffers from drifting, meaning that after the entire evaluation, the PPLU actually is not that good. And we find that the specialized VPR methods outperform the simple step MSG baselines, but AOMSG performs the best. And for the place object part, we evaluated, like I said, we evaluated with ground truth detection or with the detection from the grounding dyno. And we find that our method outperforms all the baselines. And we also find that there is a huge performance gap between using the ground truth detection and use just an off-the-shelf open vocabulary detector, which is kind of expected. But the good thing is that the performance stays consistent even with these noisy detections. You can still see that the performance that used to perform well on the ground truth detections can still perform relatively better than can still perform well on the with the detection results from the off-the-shelf model. And here comes some analysis, right? So we would like to know whether our model learns meaningful representations for the place and for the object. So first thing we do is that we visualize the learned object features, the object embeddings from the model. Here are 6 things that are aligned vertically, and we compare and we visualize it with t-SNE. So the first row is it's the result from the SAP MSG direct, where we just extract essentially just extract features from Dyno version 2 and then just visualize those features. And you can see that there is so the colors indicate different object instances, not category, but instances. And each point is an appearance of an object or a detection from one image, a detection of an object from an image. So you can see that the pre-training embeddings, the direct row, the first row, the pre-training embeddings can already give you some decent separations between these objects. And when you tune a linear probing head on top of it, the separation between the objects get slightly improved. And our model gives the most significant separation on the third row. So that's the visualization of the learned object embeddings, where we see that it definitely it actually learns some way to recognize different object instances, not just categories. And the second thing is the place part. So we know that the place. So the space is actually continuous, but place is like a discretization of the continuous space. So that involves a threshold. If the camera poses are larger than a certain translation and orientation difference, then we mark it as another place. And this is the convention, sort of the convention in robotics perception. So we would like to know. And using that as a supervision, there definitely raises a concern or question. Does the model just learn that fixed threshold, or it actually learns some concept of the space, right? So to examine that, we visualized the learned relative pose distribution, as you can see on the right, which are just histograms on the test stat, where the horizontal axis are the actual poses. The first two are the orientation differences, and the second row are the translation differences, and the y-axis are the frequencies. It's a histogram, and the blue part are those that are predicted to be connected, to be on the same place, and the red parts are those predicted to be not connected. Because so you see that the ground truth poses are on the axis, and the blues and the reds are the predicted. And the green dashed lines are the spatial threshold. For example, here in this task, we use 1 meter as the threshold for translation difference, and 1 radian as a threshold for the orientation difference. And you can see that the model makes mistakes, of course, and but they still get a clear separation between those are actually in the threshold and those are actually beyond the threshold. And this separation is smooth, meaning that the model makes less mistake when the poses are further away, but gradually the mistakes increase when the poses are drawn closer and closer, and most of those are correct with falling in the threshold. And for those are not connected, actually a huge bunch of those are actually not connected. So that means the model does not just learn a binary threshold. It is trying to learn the visual appearances and the poses and the concept of poses, and the relation between the visual appearances that you get from the image encoder and the actual pose differences. So takeaways. So our simple method AOMSG, OMSG works well. It's a reasonable baseline for this new task MSG, but there are still some gaps for improvement. We just built a very simple model. You can and we use very simple loss objectives. But in the literature of, for example, visual place recognition, there are a bunch of different kind of loss functions you can use in the tryout. So there are still definitely some gaps for improvement. And this problem of multiview scene graph is not solved yet. But we believe that it presents a means or a task to evaluate spatial, some sort of spatial intelligence or spatial representations that mimicking biological intelligence. And we present this work as a move towards learning-based topological scene representation. And so wrap up, the conclusions of this work is that we proposed the multiview scene graph MSG as a new task for evaluating spatial intelligence, and we curated a data set and designed evaluation metrics to facilitate this kind of task. And we designed a transformer decoder model, OMSG, to solve the task, which jointly learns in object embeddings and place embeddings and determine the graph based on the embedding distances. And we showed by experiments that the model is effective. And so there are definitely some limitations. For example, the data diversity is a limitation. We only used one data set that is from indoor and only containing static objects. And in the future, we plan to extend this work to more diverse data, for example, for incorporating another indoor data set like ScanNet, for example. And we would like to also incorporate both indoor and outdoor data set, and perhaps both static and dynamic objects, and perhaps just also try to detect the object changes on the graph. And also the detection quality is definitely the issue because we did not train the detector along with our model, which is simply used an off-the-shelf, very easy to use open vocabulary detectors. So the quality of the object detection definitely influenced the overall performance. But we still observe consistent performance, and it perhaps will be intriguing to try to train both of them altogether, but I'm not sure. So a final note on future applications. So after this presentation, you might be a little bit convinced that this MSG, this multiview scene graph, looks good, but you might ask, how should I use it in real applications? And my one sentence answer is that anywhere that a graph-based explicit scene representation can help, you can try out this method. For example, I can point to two directions. For one is you can do flexible local reconstructions. Sometimes you need reconstructions for the robots to actually do some tasks in the environment, but it's not always necessary to store a large scene that is reconstructed on your machine. Instead, you can just present this graph, which is memory efficient, and localize yourself on the graph. And then when you localize yourself on the graph, you can retrieve a subgraph of your observation, and then locally with the subgraph, with the local observations, you can build a local reconstruction. And then when you move on to the next location, you can still localize yourself and do that iteratively. So you don't need to always have the entire huge map of the environment if it's huge. But you can always have the graph and then flexibly reconstruct the informations at the local level. And second is that you can do embodied question answering. If you want to query a video, you want to get information from the video by question and answering. The length of the video, the context length is always a challenge, right? And MSG, the multiview scene graph, it extracts a graph which is a structured data. And if it's a structured data, then you can write functions and you can prompt the multi-model large language model to write code and call these function APIs to get information, interact with the graph, retrieve information from the graph. For example, if you have an MSG of the indoor scene, you can ask how many chairs are there and where I am, how can I get from one location to another location. These are the basic examples that you can use with the graph. And in the future, I'm trying to build a mobile manipulation pipeline that uses the multiview scene graph as the spatial memory of the robot. And so with that, it can first by answer questions from by interacting with multimodal language models, you can localize in the model. The robot can localize itself on the graph, and then you can tell the task to the robot, and then they can plan a path on the graph, and then from on the path it can navigate topologically, when it reaches the target node, it can build a local reconstruction, a flexible local reconstruction, and then it can conduct some manipulation task at that location. So these are the possibilities that I can think of for utilizing this multiview scene graph. Yeah. Okay, almost on time. So basically that's it. Welcome to scan this QR code to check out the website of this project. And our code and data are also accessible from there. Thank you.
Fantastic. So we'll go ahead and include all these, all the links in the follow-up email, as well as a link to the playback. We've got a few questions that came in here. Let's go ahead and tackle them. This first question kind of came near the experiment result analysis section of the talk. Unreal and Omniverse feature scene graph representations at some level of functionality. Is this useful for simulated training testing? For example, ground truth, or are these game engine scene graphs somehow not useful?
Good question. I'm not familiar with the scene graphs from Omniverse and Unreal, but I think definitely you can leverage all kinds of graphs or object and place information that you can get from both simulation and real world. Currently, the method is a supervised training, so that means it's difficult to generalize to untrained or unseen objects. It'll be interesting to try it out when you can include simulated data. You can include arbitrarily large number of objects and different visual appearances of places, which could probably make the model more generalizable.
All right, and this question came at the conclusion of the talk. Does the shortest path between place nodes in the graph also represent the shortest path and distance in the actual scene?
That's an interesting question. Ideally, I don't think it's necessarily the same thing, because if the graph is binary, then there's a chance that you see you're in the same place, but this node is this image is just a little bit closer by than the other image, or the other image also sees the place, but it falls into the same threshold, but it's just like a little bit further away. So if you just use the binary outcome, then probably it's not the same shortest path. But I guess if you use the feature, you should just measure the cosine similarity. Perhaps this node that is closer by has actually a larger cosine similarity than the other node, which is also connected, but has a smaller similarity. So I guess if you use a weighted graph where the edge is a cosine similarity, then perhaps the path is closer to the actual the shortest path is closer to the shortest distance in real world. But I'm not sure about that because it's learning based and there's no metric information involved throughout the training pipeline. So I don't think there's a guarantee that the cosine similarity is always correspond to the actual geographical or metric distances.
All right, and this final question came early in the presentation. Is there a connection between the multi-view scene graph and the representation learning in which each object is encoded as a vector in latent space and a decoder mapping the latent representation to an image?
I agree with the first part. When I design this architecture, I'm trying to my inspiration or my motivation is basically from the representation learning side. I want to instead of just directly build a graph, I want to learn the object features that are view independent, and I want to learn the image features or the place features that are like spatially aware. So I'm trying. So the model is exactly learning representations. But for the second part of the question, a decoder mapping the latent space to an image. So the decoder is decoding the queries which attends to the image features, and the queries are object queries and place queries. The outcome of the decoder is those place embeddings and object embeddings that are like context aware, that know information from the image, but it does not actually map the information back into the image. It will be interesting to see if you can use the outcome, use the embeddings that you obtain from the model to back attend to the image features and maybe compute a heat map, just like a previous presenter showed. Maybe by that you can kind of localize an object on the image. It will be interesting to try it out.
All right, maybe one last question here before we let everybody go. How can different sensing be added to this scheme? I'm assuming
Sensing.
beyond I'm assuming beyond vision, I suppose.
Yeah, what I can instantly think of is something like depth. Depth is also kind of another sensor, right? I guess adding depth to it would definitely help, because if you have depth, you can essentially build 3D scene graph. You have depth, you have RGB, you can try to do reconstruction, and with reconstruction you can already build 3D scene graphs. And there are a bunch of work along that line. You can search for 3D scene graphs and incremental 3D scene graphs from RGB sequence. Here we just don't assume that we have depths, because we think that there are just abundant of videos online where you just take the videos with your camera, with your phone, with your iPad, and you don't upload the depth information along with that to the internet. So it would be beneficial to just have this sort of topological graph from purely RGB inputs. Other than depths, it's hard for me to instantly think of a way to incorporate sensing signals like, I don't know, like sound. I'm not sure about that.